Hello, welcome to this tutorial on cross-weather and time long-term visual geolocalization. My name is Rakesh Teddy Kumar, and I work for SRI International in Princeton, New Jersey. The topics I'm going to cover are related to coast search, which is essentially being able to find an image in a database of images and then find geolocalization. In each of them, we are trying to locate where the image was taken from in each of these cases. In the coast search, you are searching amongst a database of images, you find the closest one, and then you say this image was taken somewhere close to this one. And in find geolocalization, the goal is to find the exact location, the latitude and longitude and orientation of the camera when you took it. And for both of these, we're going to talk about different aspects of current techniques based on deep learning. And then finally, we'll have some concluding remarks. So the topics I'm going to talk about essentially cover 7 papers. 4 of them are in coast search, and 3 of them are in find geolocalization. And essentially, I'm going to walk you through a sequence of developments which have happened over time in this area. So image-based geolocalization, given an image, like this image over here, the question which is asked is, where is this image taken from, right? So you can guess maybe it's at this location, or maybe it's at this location. And so what we want to be able to get is the exact location where this image was taken from and the orientation. And that's what image-based localization is. In this talk, we're going to talk about how to solve this problem in one particular way. But this whole tutorial is about how to solve this with different methods. The method which we're going to solve in this one is shown over here. We are representing the world by a set of geotagged images. So we've taken a lot of images from all over, and for each one of them, we've noted the latitude and longitude, the position from where this image was taken, and the altitude, and the orientation. And then the task is to find this new image by matching to these and saying, okay, I match closest to this one, and so my location must be very close to where this one was taken from. And why is this a difficult problem? It's a difficult problem because the appearance of images can change quite a bit. As you can see over here, it can change due to weather, seasons. You can see winter and summer, fall and spring, day, night, and then also occlusions. Like here, there's a big truck blocking the field of view for this building over here. And so these are all challenges for solving this problem. Also, it's a big data problem because we're trying to find this image in a world of images. So there are lots and lots of images. You need to be able to search this image through that to be able to say, this is the one it's closest to. And as we'll get to it, we not only want to find the closest image, we actually want to find the exact pose. And so the second set of techniques will be based on that. So there are a number of data sets which have been collected for this, for visual place recognition. And these people have been collecting data sets all the way from 2007. And they both are urban, outdoor, there are even some indoor ones. They are, a lot of them are in cities, but there are some which have a wider outlook. They're not just restricted to cities. And they're also for different challenging conditions, day, night, winter, summer. And they have different types of ground truth, GPS in many of them, the pose of where the camera was, or just labels. So the techniques which are used for these, the typical technique is, given the database of images, you generate some image representations for each image, and you store them in a database. Given a query image, you generate an image representation, and then you do some kind of similarity search and come up with candidates. So So it's very similar to doing Google search. You type something in, and it's going to come up with candidates. Here you're putting in an image, it's searching through the world of images and coming up with candidates. And then you can have some refinement on these to say, okay, these are what the first steps are due, the first, second, third. And by doing this refinement, you can come up with a refined first, second, third. So this problem is called visual place recognition. And I'm going to describe to you over here two methods. One is the classical architectures for solving this problem, which are on the top row. And in the bottom row is solutions based on neural networks. And essentially now I'm going to talk about a very influential paper in this space called NetBLAD. As you'll see later on, even in the subsequent talks, NetBLAD has been used by all over the place for lots of methods as a base method. So given an image, you run some kind of feature detector. So here on the top, we are running a SIFT feature detector. You're finding interest points, and in each one of them, you're computing a SIFT. And in the bottom, you're running some kind of neural network and coming up with some neural representation of the image. And then given this neural representation or this list of features for different points in the image, you do some kind of aggregation. So we're going to study in the next few slides how you can aggregate them with things such as bag of words, GLAD, and things like that, or how you can do them some aggregation using neural networks. And essentially, we'll talk about how NetBLAD does this. And then you come up with a vector in the end, which represents this image, right? So the advantage, of course, of the neural network approach, the one below, is that it's trainable end to end. In the top, the more classical approaches, there's a particular way to implement SIFT. So there's no training there, you're just implementing it and using the features which you get from it. And it's giving you a particular way to aggregate the features. So there's no training over here. While here, all the weights of this network are learned by giving it positive and negative examples. So let's just review some of the past techniques. So when one of the initial techniques was the bag of words technique developed by Civic and Zisserman in 2003. And here the idea is you've found these feature points in the image. At each one of them, you've computed the SIFT feature. And then you've taken all of them and divided the world of features into bins. And you place any one feature into one of these bins. So here, if you have multiple features, they're being placed into different bins. This bin has two of them, this bin has one, this bin has one. And essentially, the feature representation is the histogram, the number of feature vectors which lie in each bin. So there's one in this bin, 0 in the next bin, 2 in the next bin, 1 in this bin, and so on. So this histogram representation of number of features in each bin is what was used in the bag of words to represent this image. There was an improvement to this method by a technique called BLAD, vector of locally aggregated descriptors. And here, besides just placing the feature point inside one of the bins, you can also calculate the residual vector from where the feature point to the center of the bin. And that's given by this xi minus ck. And the 0, 1 assignment is to which cluster it lies, right? So this bin, at this point xi, if it lies in AK, cluster k, it'll be 1, and for the other clusters, it'll be 0. And so then you can represent the image by the sum of over all these descriptors in the image, and you come up with a vector representative image like this. And you can see over here, if 2 of the points fell in the same bin, then you take the aggregate of them, the aggregate of the residual vector to represent the value at that bin location. And now you can search with this vector representation, the vector of locally aggregated descriptors. And this was shown to be much better than VLAD because it has much more information. So now you can make this, here you're doing a hard assignment. You're assigning a point to one of these bins. The next technique, the technique I'm talking about over here, NetBLAD, which was developed in 2016, I noticed Civic was the author of the bag of words too. This NetBLAD technique, you don't do any hard assignments. You say, okay, this point could lie in this bin, but I don't know whether it's going to lie in this bin or not, so I'm going to do a soft assignment. I'm going to give a certain weight to whether it lies in this bin, and then if it lies in this bin, this will be what the residual is. So you're replacing hard assignments with soft assignments using the softmax term over here, which is in this yellow box. And so using the softmax, you get residual vectors at each one of these. If there's a strong likelihood it lies in this, then this will be very high, and the residual vectors at the other places will be 0, or close to 0. But the point is, you're not making a choice up front. You're letting the system learn where this feature point should best lie. And so in the NetBLAD, you're taking an image, you're running the convolutional neural network, and then you're doing the soft assignment of all these feature vectors to these different bins, and then using that to compute the softmax, and then using that to compute the VLAD error function. And then that gets normalized, and that's the NetBLAD vector, right? And this is what you search. So, and to train it, you give it a lot of positive and negative examples. And for these kind of ranking problems, people have typically used 2 types of ranking loss. The first is pairwise ranking loss using Siamese networks, where you either give it a positive image. So here I'm trying to learn how to recognize Steph Curry. So when I give it positive examples of Steph Curry, and I can give it negative examples. So if it's a positive example, I want the different images of Steph Curry to lie close in the embedding space. For the negative example, then I want the image representation, feature representation of Steph Curry to be far away from that of Klay Thompson. And that will let me use this technique for training it to search for faces. Now, so here I train it with either a positive or negative pair, or in the triplet ranking loss, you give it both positive, negative at the same time. And then you have an error term which combines both of them. If it's a positive one, then you're adding the error term. And if it's a negative one, you're subtracting it. You know, the maximum is 0, and you have a margin of m. And so you use this to train with one of these methods. In this paper, the NetBLAD, they use the triplet ranking loss. And you can see with the results over here, the slide over here, they get very good results. So it was trained on a database of 76,000 images for this test set over here, and from Street View, and queries with 315 images from mobile phone cameras. And these are images taken at day, sunset, night, etc. And as you can see, there's a 35% improvement over the previous state of the art, right, at the recall at top 5. And you can see that also by the curves over here, where the NetBLAD is this red curve, and that's being compared to these other curves over here based on different methods. So that was NetBLAD had very nice results. And as I noted earlier, it's a technique which has caught on, and people have used it even for the other problems which you learn about later on, such as cross-view and cross-modal geolocalization. So a general deep learning based architecture for global search, these are the steps. You know, you have some kind of convolution happening. Then you use that to compute features. Then you do some kind of aggregation. And then you do some kind of normalization of it. And this is the vector which you get to represent its image. And then you're going to train a system to a neural network where you're going to train all the weights for this convolution, aggregation, normalization, etc., to come up with the best feature vectors for this image. So to train it, you have a choice of the error metric. We talked about two of them already, the Siamese training and the triplet loss. And then you have to train it. So you have to give it positive and negative examples. So how do you train it also has been studied quite well. So we'll talk about each one of these now in the next set of slides. So the next talk I'm going to cover, which actually happened a couple of years later after the work on NetBlad, is this work on fine-tuning CNN image retrieval with no human annotations. It's published also in PAMI 2018. So the overall architecture is given over here. Given an image, you're doing some kind of convolution. And then they have an innovation. They have a new method of pooling called generalized mean. We'll read about that in the next slide. And then they have a method for doing normalization, which they adopted from previous works. And they come up with a descriptor. And they use the Siamese learning method. And so they have a particular way in which they choose positive and negative pairs. And they show in their paper that if you choose the positive training pairs and negative training pairs intelligently, you can greatly speed up the performance of the training, both in achieving lower training errors and also training more quickly. So for pooling with image representations, the normal methods is you have an image, you run it through the convolutional neural network, you have a bunch of features at the final level. So these are the features or filters from say x1 to xk. And to come up with the image descriptor, you do some kind of pooling across these filter values. And one popular method used is max pooling. Another method uses sum pooling. So max pooling, you take any particular image location and you compare it across all these different filter values and you pick the max one. And the sum pooling, you add all these images up and then you average them, right? And the observation is that max pooling is more invariant to scale changes, whereas sum pooling is less sensitive to distractors and feature maps. But generally, these are fixed. So you either do max pooling or sum pooling, and you're making a choice of which one you're doing. So these folks in this paper did not want to make this choice. They wanted to learn that. So they came up with generalized mean pooling. And that's given by this equation over here. In generalized mean pooling, what you're doing is you're essentially taking the feature vectors and taking them to the power p, summing them up, and then taking a root to 1 over p across all of them. So if you look at this equation over here, if p is infinity, then this would be the same as max pooling. And if p is 1, this is sum pooling. In this case, in this paper, they make p a trainable value. So when you train it, you also solve for p. And that will tell you what's the best P to use in any particular situation. And that's what you see in these results over here in this slide, that they show the results across different data sets, Oxford 5K, Oxford 10K, etc., with both max pooling, sum pooling, and generalized mean. And they show the initial values and also the learned values. And you can see there's a good jump in performance by about at least 5 to 6% between the methods which don't have any learning in them versus the methods which have learning. So this was a nice advance which was done by this fine-tuning paper. The second thing which they did was they actually normalize their feature vectors. So if you have the highly dimensional sparse representations, then the results aren't as nice as if you normalize them. And to normalize them, you go through these 3 steps. You center them, and centering helps emphasize negative evidence and also has high importance of jointly missing visual words. And then you rotate it so that it correlates the different dimensions and allows us to remove least informative dimensions. And then you whiten it, which is what you're seeing over here. So you're making the representation normalize in all the different directions. And it's also centered across, around the origin. So they also show doing this normalization helps a lot. The third thing which they innovation they had was how to train it. And so they're using the Siamese network, but the question they're talking about or discussing is how do you choose the positive and negative examples? So in the Siamese network, if you remember, you can train with a positive example, a negative example. If you train with a positive example, you're adding it, the error term. And if you train with a negative example, you're subtracting it. Really, how do you choose these positive and negative examples? And they show choosing wisely makes a big difference. So negative examples, they try and choose negative examples which are diverse. So let's look at this top row over here. There's the query image, and you can see if it's a spiral staircase going down. And if you just run the system without training or with very little training, you may get a descriptor like this, which is actually a piece of art, which has a circular thing in it, but it's coming up as a top hit for this query. Now, if you choose other, like these ones in this column over here, these are in the same, very close to the top, this one, the most similar CNN descriptor. So if you also train with these, you're not really getting any more information. So their idea is you take all the training data and you organize it into 3D different clusters, into clusters which are co-located or in the same area. And you only try and choose one for each cluster. For each cluster, they build a 3D model. And then they say, oh, we'll only choose one negative from each one of these. And they want to choose hard negatives. So they choose negative examples which are closest to the query. They know they are negative, but their feature value which has been computed, the feature vector is closest to the query one. And so you want to choose those because those are going to have the biggest bang for the buck. So what they say is only good hard negatives is as good as using all negatives, but much faster in training. Similarly, for positive ones, you try and choose positive examples that share 3D points with the query, but you want to choose positive examples not close to the query. So you want to choose positive examples whose feature vector is much further away from the query one, because again, training with them is going to give you much bigger bang for the buck. So in this slide over here, what I'm showing is, this is from their paper, what they're showing is the improvement in training as you train more wisely. If you choose harder positives, which are not close to the query, or harder negatives, which are closest to the positives, you can see you get these top two curves, this red, pinkish red, and purplish blue one right on top. While if you just use the vanilla approaches, you get something at the bottom. Okay, so that was it for this paper on fine-tuning CNN image retrieval with no human annotation. Now we're going to go to the next topic, which is on rank loss functions. And we're going to talk about pairwise ranking and triplet ranking. We talked about these already. And this is what people have been using to train these neural networks for ranking. For retrieval. And in this paper, which I'm going to talk about, smoothing AP, smoothing the path towards large scale image retrieval, I'm going to talk about doing this with minimizing average precision. And this was a paper which appeared in the European Conference on Computer Vision in 2020. So here the goal is to use average precision, and they say average precision is used to benchmark retrieval systems. So let's understand that. So this is a query, and you can see these are the different returns over here. And the first and second returns are pretty much the same animal, deer-like animal as the query one, while the third and fourth, the third's the bunny rabbit, and the fourth, they are both not deers, while the fifth is. So first, second, and fifth are positive returns, while third and fourth are negative returns. So the average precision is given by this equation over here, where 1 over, what you're doing is you're going over the space of all positive returns and calculating the rank first of all the positive returns amongst themselves. So this one was first, second, and this was the third positive one. And in the bottom is the rank of the positive one amongst all the returns. So if you take this first one, it's 1 over 1, because it's the first positive and first amongst all. The second image is 2 over 2, while the third positive is fifth over all of them, so it's 3 over 5. So for average precision, you calculate this average all the way through for all the returns. And if everything was perfect for all the positive returns, if everything was perfect, there should be 1, right? So the lower this goes, less than 1, that means you have more and more negative examples being ranked higher than positive examples. So the goal of this paper is to optimize a smooth version of this average precision. And as you'll see, they show that this does much better than minimizing either the triplet loss or the Siamese network, which are not really measuring, helping you minimize what you really care for, which is this average retrieval precision. So to calculate the average precision, what you can do is, say you want to calculate the average precision for this fifth return. It's 0.24. It's similar, its value. So you can subtract it, the 0.24, from all the other ones which have happened so far and afterwards. The ones which are ranked higher than 0.24 will be greater than 0. While the fifth one, if you subtract 0.24 from it, it will be 0. While all the ones which ranked earlier will be greater than 0. And all the ones which ranked less will be less than 0. So now you convolve this with this Heaviside function, which is 1 for everything greater than 0 and equal to 0, and 0 for anything less than 0. So if you convolve these subtracted similarity scores with this Heaviside function, you'll get the value 5, which is the rank. So what they said was, of course, this is this is given by this first equation over here. This, if you can minimize this, it'll optimize the ranking metric, but unfortunately, this is not differentiable. So what they say is that you can replace this with this kind of function, smoothing function over here, which approximates this. And by increasing tau, the more you increase in tau, the sharper this will be. So you can increase this average precision loss by the smooth average precision loss by using this function. And this will now be differentiable. In contrast to the ranking surrogate loss, which is the triplet loss, which you cannot, which is differentiable, but it does not optimize the ranking metric. So what they showed in this paper, they use this technique. You can apply it for all kinds of retrieval problems, not only localization-based retrieval problems. And they showed they got a good bump in performance by minimizing the smooth AP. Just to give you some intuition about this technique, this slide is from their paper and gives a very nice intuition. If you look at this query and this retrieval, you can see these are the different similarity scores. Now, if you wanted to optimize this where, say you had two options to optimize. One was to bump this up, its score by 0.02. And the other was some return over here to bump its output by 0.13. you can see this is another value which you're bumping it up. But you can see by if you do option 1, is the rank is going to change, right? While with option 2, the rank is not going to change. It's going to still remain the same. So the option 1 with the smoothing error term in yellow, you have a large change in loss because the rank changes. For option 2 with the smooth one, you have a small change in loss. While for the triplet loss, for the first one, because there's a large change over here in the score, you get a large change for the triplet, but a very small change for the triplet for the option 1. And so with the triplet loss, you're going to favor doing option 2, which is really not helping you in any way in increasing the ranking performance, while with the smoothing AP, you're going to favor option 1. So they tested this technique on a variety of retrieval problems. I'm just showing you results from their paper for one of them on iNaturalist. And you can see from this table over here, this is the record at K for different methods, and their method, which is in the bottom row over here. And they're getting a good, at top 1, they're getting a good 5 to 7% performance compared to previous methods. Okay, so that was on how to minimize, right? And using smooth AP as an error metric is much better than using Siamese networks or triplet loss. And there have been many techniques for this average precision. I just presented you one of them, which came out last year, which I thought was very elegant and simple to implement. Okay, so now we're going to change tacks and speak about a different thing on cross-term geolocalization using semantic cues. So here, the goal is, again, the idea is problem is the same: geotag an image for retrieval from a database of images of known locations in the presence of large appearance changes across weather and illumination variations, which you're seeing over here, like day, night, winter, summer, things like that. And the goal, the way we plan to do this over here is, again, using embeddings, using deep learning. But what we did here was collect images from webcams for training. So we took static webcams, 2,685 of them, and collected about 2 million images. And for each of those images, we now have data 365 days a year and 24 hours in the day. So we have a lot of data across all kinds of course, day, night, weather, different days of the year, but also different, it could be raining sometime, it could be snowing, things like that. And we have two innovations in this paper. One is to use semantics, and the second is to use attention. And we evaluated using both of them. So given the image, the RGB image, we also run a semantic segmentation network, and then we feed both the ordinal RGB image and the semantic image to this attention-based semantic fusion network. And I'll describe that to you in more detail in the next few slides. And then we use that to then come up with a vector representing this image, and then we do this online triplet loss to train the neural network. So I'd like to show you this image. This is semantic segmentation of video for a similar route for this site taken in summer and winter. So you'll see as I play the video, in the winter, there's snow on the ground, the leaves don't have trees. In the summer, it's all green, the leaves have trees. On the right-hand side, you have semantic segmentation. And you can see it looks fairly similar. It's detecting roads, buildings, trees, things like that. And you can see that as I play the video. It looks fairly similar in many places. Of course, this is a different time of the day, so the different cars parked, but you can see it looks fairly similar as I play the video. So the first innovation which we did was previous networks were just using the RGB image. Now we explicitly compute the semantic neural network and feed that as a separate thing in parallel with the RGB image. And the spatial layout of the semantic classes in the image lead to descriptors which have much higher invariance. So, the system will automatically learn, okay, I should not use trees as a feature representation because they change a lot. Or if I'm seeing a car in the scene, it should not be very useful because the cars always keep changing. You may or may not have cars in the scene. So based on semantics, it learns what to pay attention to and what not to pay attention to in the image. And so this is a full system. You have the RGB image and semantic feature maps. They are fed to this fusion network where we take features from both of these and concatenate them. And then we feed them to this channel attention module, which helps to pay attention both spatially and also across the different channels. And then we take that and get attention for both the RGB image and the attention map, and then multiply the semantics map with the attentions and the RGB image with the attentions, come up with refined feature maps, which we then concatenate and run through some fully connected layers to come up with the final representation. And you can see both here query, image, and the techniques produce the result, the ground truth. And then these are the appearance images. This is the semantic segmentation. This is the semantic attention, appearance attention. The best return from another technique, MS not related to ours, is about 13 kilometers away. Well, ours, by using these things, we're getting a return about 212 meters over here. This return is 212 meters from this one. So what I'm going to show you here is a video where we ran this, where we trained the system during winter time with images taken at the winter time. And on the left-hand side is the video we are testing at the summertime. And for any one image, we're showing the top 4 returns, which are shown over here. And if any of those returns are within 6 meters of this image, we put a green box around it. So you can see these 3 returns have a box around it. I guess it's less than 10 meters, then we put a box around it. And if it's more, then we don't put a box around it. And as I play the video, you'll see we mostly keep getting green boxes, and the system does really quite well. We also do this at the nighttime. Data set with matching day to night. So these are images taken at night, and we built a database with this using that semantic attention technique, SANE. And now we are matching query image to that using SANE. And again, if it's within 10 meters, it would be all green all around. And you can see that it's mostly green, which is kind of amazing because even for humans, these tasks of matching day images to night images can be quite complicated. Okay, so that was another technique for coarse search, and we got very nice results, and it also improved the performance of NetGlide quite a bit. So now I'm going to change tacks and speak about the next part, which is fine geolocalization and end-to-end solutions. So previously, given an image, we were finding the best candidate matches. Now what we want to do is get the exact pose. And all the techniques have a similar flavor, but different methods to do it, but similar sequence of steps. So you do some image retrieval by search from the database to come up with candidate matches. Then with those candidate matches, you detect, describe, and match features to those candidate matches, find features, and come up with correspondences. And then you do some kind of resection to compute the pose. So here you're doing the image retrieval. Then you're doing the feature correspondences between different candidates, which is what you're seeing over here. And then you're calculating pose by resection. And you can calculate pose just using one image or multiple images in the sequence. You use a similar kind of technique also to build a 3D map of the area, because if you find lots of images that are matching to each other, then you can use that to do a bundle block and recover a 3D model map of the area. And given all these point correspondences to doing this bundle block and building this map of which calculates exact pose and the 3D point cloud and all, there's a very popular technique out of UNC called call map, which a lot of people use, as you'll also see in a few minutes. So the first paper I'm going to talk about was by Sarlin and all, from Course to Find Robust Hierarchical Localization at Large Scale. It was presented at CVPR in 2019. And they have the 3 steps which we talked about. There's a global matching step, is used to retrieve a bunch of candidates. There's local matching between this image and those candidates to come up with point correspondences. And then those are fed to a module which computes the pose. In their case, they want to run the system on a cell phone, on a smartphone. So they want it to be very efficient. So what they do is they share the basic neural network for both the course search and the global descriptors for the course search for, and global descriptors, and for the final alignment, the local features. They share a basic network for it, which is what they're calling HFNet. But then what they do is they have different heads. They have a head for the global search, which produces the global set of features which are used for indexing. And then they have also a head for producing local features, which are then used for doing the 3D fine localization. And you do this both for the offline data and also for the online data when you're doing the query. So with the offline data, you're building up this global index database with the training we talked about. They actually use NetBlad, and they also build up this local feature representation. And then given correspondences with the query, they do this fine pose estimation. And that gives you the exact location. And so to train it, as I noted earlier, they use NetBlad, but they use a mobile version of NetBlad which can run on a smartphone, and it has many layers. So you use this mobile net, and then that is fed to a NetBlad layer to compute those aggregate features. And they also tap this mobile net at midway to another technique called superpoint to be able to compute the superpoint, use the superpoint decoder to compute the local descriptors and the key points. So these two things are telling you, key points are telling you where features are located, and local descriptors are giving you the descriptor at each one of these. These will be used for doing the local correspondences, and the global descriptor from NetBlad will be doing the search to come up with it. To train it, they have a very nice technique, but what they do is they say it's very difficult to kind of database which has all the ground truth values for both the local descriptor, the local matches and also the course matches and all this. It's very hard to come up with the data for training that. So which has both the things at the same time. So they have 2 models, a global teacher model and a local teacher model. They train the global teacher model with these global data sets, and they train the local teacher model with the local data sets, and they are basically training them simultaneously. They'll feed data for training the global teacher model. They'll feed data for training the local teacher model. And so they have these 2 teacher networks running simultaneously. And this is called multitask distillation to learn this more compact neural network, which can run on a smartphone. So these are their results. This is one set of results they have over here. Run on these different data sets, HN, robot car, and CMU. And if you look at the bottom two rows, NetRad and SuperPoint is their technique without sharing the network. And by having this HFNet, which is sharing the initial part of the neural network, both for the course search and the fine alignment, it's a much more efficient implementation which can run on a cell phone. So the bottom row over here can run on the cell phone, and the NetRad plus SuperPoint is an upper bound for their method, because this is approximating that. And you can see, firstly, the best results they get are by this combination of NetRad and SuperPoint. It's a good bump in performance across the different methods. And the HFNet is fairly close. Their results are recall. Over here, I forgot to say this, at different distances and orientations. So they have distances of 0.25, 0.5, and 5 meters, and orientations of 2, 5, and 10 degrees. So when they say they get 79.7% or 75.7% accuracy here, this is for the returns which are within 0.25 meters and within 2 degrees. And so you can see what the results are. You can see they do very well during daytime for this data set, but do quite poorly at nighttime. Okay, so the same author, one of the same authors, Salin, actually came up with another method in CVPR 2020, which is very nice. It's a great paper called superglue. And this uses context to do the local matching. So you have the CNNs, you're computing some local features, and now you're using a graph neural network to come up with the strong matches between two images. So for the local matching, the typical steps are given by this row over here. You first do some detection of features from the image pair. You describe those features. Then you do some feature matching. Typically, people have used nearest neighbor, things like that. Then you do some outlier filtering, like people do ratio test, mutual check, or you can learn it. And then you do the final pose estimation. So what they're doing in superglue is replacing 3 of these boxes of superglue: description, feature matching, and outlier filtering. They're still doing the detection. And you'll see they've tried different methods. I think they find SuperNet gives them the best results. And instead of doing nearest neighbor matching, they're doing this learned thing based on their classifier. So to motivate superglue, what you have to do is look at this example here. We are trying to match checkerboard images. And you can see if you take any one square here and try to match it with this image over here, it's quite difficult. All these squares are very similar, corners are similar. So any corner here could match to any other corner. It's only when you take all the aggregate of these corners and try to match them all to each other, then things fall in place. And that's where the importance of context is. So if this point matches to this point, then that point should match to that point, right? So that's what context is. And superglue helps you take advantage of this context by doing attention, by doing both self-attention and cross-attention. And as you know, attention is a big buzzword in neural networks nowadays. So superglue is a very nice paper using attention. It's not using transformers. They have their own method, and it's really quite nice. So what they do is they do both self-attention and cross-attention. Given the local features, you both have a visual descriptor and a position encoding for where their descriptor is. You represent it both for 2 images, say the query image and the reference image, A and B. And then you do self-attention for each of these features with each other in the image, in each image. And you also do cross-attention. Okay. And so these attention things encode the contextual cues. You use these, you come up with this representation which is encoding this attention to come up with matching descriptors. And then you do matching across these. So you come up, you have the initial feature representations, you do this attention aggregation, you come up with new feature descriptors, and now you have the score matrix which shows how each one of these features matches with each one of these features. So you have all the features in image A, you have all the features in image B, and the score matrix is saying how each one of them matches to the other. You also have a dustbin which says any one of these features may not be matching to anything in the other image, so it would go into the dustbin. And they use this synchron algorithm to optimize this matrix with the score matrix they've computed over here to come up with partial assignments. So they have two neural innovations, a graph neural network with attention to come up with descriptors, and then this synchron algorithm using to do the assignment. So in this image, you get an intuition about self-attention and cross-attention. So here for self-attention, you can see this feature is relating to other features in the image. And it's giving the ones which are more reddish and bolder, it's paying more attention to. And then you can see in the top row, these are self-attention. And then you can also see in cross-attention in the bottom row, where from one image to the other, you can see, for instance, it's paying attention to different points in it, and they have different values. So in this representation, you learn for each feature, its representation is also guided by how much attention it is paying to other features in the scene in the matching image. And then, as I said, this is fed, these matching descriptors are fed to the score matrix with dustbins, and then you use the score synchron algorithm to come up with these partial assignments, and this whole thing is differentiable. And using these partial assignments, they can come up with the correspondences, and they use these correspondences, they train it by computing ground truth correspondences. So given the correct pose and depth, they compute ground truth correspondences, and they train it by matching to these ground truth correspondences. And they get very nice results. You can see that over here. They're matching these two images. They're from the viewpoint has changed quite a bit. It's also day versus night, and they're able to establish very nice correspondences. Again, this is an indoor image. One, you're seeing the right wall, and the other one, you're seeing the left wall, but still they're able to match them quite well. Salin took part in a competition both in CVPR and ECCV, and this particular set of techniques won first place in 6 of them last year. And so he had a talk on that, and these are some slides from that talk. He had a toolbox called H-Locks, which is a toolbox for basically building up this localization and the database. So given the database images, you build up a 3D representation, again, by doing the superglue to find matches, and then given those correspondences, you use a call map, which I talked about earlier, to build up this 3D reconstruction. And then given a query image, again, use H-Lock to come up with correspondences, and then you do this pose estimation with that. So given, first you do image retrieval, and then you do the feature matching. And they tried different things for the feature representation. They tried superpoint, they tried D2net, and for the feature matching, they tried nearest neighbor and superglue. And then you do the localization. So given a query, they retrieve about 20 to 50 candidates using NetPlad. Then for each one of these 20 to 50, they run superglue to come up with correspondences. And then using that, they come up with the best matching score and the best pose. And they do the same thing for indoor data sets too, where instead of the 3D model which was built earlier based on a lot of images, you have LiDAR to do the lifting. Essentially, given the 2D to 2D matches, you lift them to 3D using either the 3D model which is made for the images or for LiDAR which is made for the indoor data set in the examples they ran. They've also done it with multiple images. So they were saying that when you have, say, for autonomous cars, you have images looking forward, images looking left and right. They were saying it's very useful to use images looking left and right because they help you place where the vehicle is laterally much more accurately. If you just use the image looking forward, then it's harder to get the placement in all directions accurately. So this technique lends itself to using multiple cameras quite easily. And as you can see, they get really good results. These are comparing different techniques for this ECCV challenge last year on handheld devices. And red is their technique. And you can see it's like the top one for many of these tests, day, night, outdoor, and indoor, in-locker, different tests. Another technique in which you can notice which did quite well is this one called captive fusion. And I'll briefly talk about it in the next few slides. So captive fusion is another technique. It has the same basic ingredients. You do retrieval using a technique which is called AP-GEM. So this has this generalized mean pooling and uses average precision. We talked about both of these. They have their own method for doing generalized mean and average precision, but they're using both those things to do the image retrieval. They use a technique which they developed called R2D2 for describing the images for local alignment. And then they use call-map, just like the other techniques. And so they again build up a 3D map from the training images. You extract these local descriptors, extract global features, compute training image pairs, compute local descriptor matches, and use call-map to build up these 3D reconstructions. And then when you have to localize, again, use this image retrieval using AP-GEM to come up with candidates. Then for each one of them, use R2D2 to get different 2D, 3D correspondences. Use call-map to come up with the pose. And then you look at the error metrics, you choose which are the best ones. And then you pick the best one to get the actual location. And so they have a series of papers to describe their techniques. And this capture paper, which is referenced over here, summarizes it all and puts it all together. And they've done also quite well in these tests. So to conclude, I went through both techniques for course search and fine alignment. NetPlad has been a very influential technique, and you'll see it has also used a lot in the subsequent talks. Minimizing AP precision gives a good gain for ranking problems as compared to triplet or Siamese networks. Learning pooling choice versus committing to max or sum. Learning pooling choice for generalized mean gives much better results. Learning end-to-end makes a big difference, and that's, of course, what deep learning is all about, learning end-to-end. And also by learning end-to-end, you can come up with joint representations for both global features and local features, which will enable much more compact networks which can run on mobile processors. And also you can use teacher networks to train them, where you train the global features with one network and the local features with another network. And finally, attention methods help provide context in matching. And these are useful both for global search and also for fine alignment. And I talked to you about the same method which uses semantics and attention for ghost search. And then I talked about superglue, which used attention and context for fine alignment. So thank you. That is my talk. If you have any questions, you can put them in the chat.